G'day, in this video we're going to be looking at how we go about classifying different types of stars and plotting them on something called the HR diagram. This video unpacks dot point 8.1.45 and 6. We're looking at the evidence that there is for the origins of the elements. Essentially, many of them come from stars. So in this video, we're going to revisit concepts around the emission and absorption spectra of stars and how we can analyze that spectra to learn more about stars in our galaxy and beyond. We're going to look at the features of stellar spectra and how we can actually use that to group and classify stars, and how that all fits with the Hertzsprung-Russell diagram, the HR diagram, which can help us to understand and visualize characteristics of stars where they sit in their evolutionary stage. And that's based on properties such as surface temperature, color, and luminosity. So in order to get through all of that, we're going to look at HR diagrams and the measurements that feature on those diagrams. We're going to look at some of our nuclear processes like the CNO cycle and the proton-proton chain and see how that can be reflected in the position of stars on the HR diagram. We'll have a look at why stars come in different shapes and sizes and talk briefly about some of the key ideas that dictate the life cycle of the star. So from previous lessons in Module 7 and 8, we know that when we analyze stars, we can have a look at the wavelength of light which is emitted, which has maximum brightness. The star itself emits a continuous spectrum of electromagnetic radiation, but as the temperature of the star increases, lambda max, the wavelength again at which there is the highest emission of light, will decrease and shift towards the blue and beyond parts of the spectrum. Another feature of stars that we can have a look at are their brightness. And while that is most definitely true, it can be a little bit difficult to compare the brightness of stars as observed from Earth. And the key reason for that is that the stars themselves that we observe are at significantly different distances away from the Earth itself. And effectively what we're applying here is the inverse square law from all the way back in Module 3. In short, essentially, the further away an object is, the dimmer it becomes. Essentially, the brightness that you observe of a luminous object is inversely proportional to the square of the distance away from the source. So when we observe stars on Earth, we are observing the apparent magnitude. Just to note, magnitude is an alternate word that is used in astronomy for brightness. So the apparent magnitude is what the star's brightness apparently is, again, based on those Earth observations, and cannot account for distances between the Earth and the star. We might see a star that's really bright, but compared to others, it may not actually be that bright. It's just simply quite close to the Earth. And conversely, we could have, one of the brightest stars in existence not look very bright in our night sky simply because it is so far away. This makes apparent magnitude quite a terrible way of comparing stars in any meaningful way. So instead we use absolute magnitude. This is essentially the brightness as observed from a set distance away from all stars. So this is a standardized distance that can be used, allowing us to compare each star to each other. Essentially, the larger the absolute magnitude, the more energy that's being released from the star. In order to determine absolute magnitude, you first need to know what the apparent magnitude is, as well as the distance away from the star, so that you can convert that apparent magnitude into one which is absolute by employing the inverse square law. While these elements aren't directly a part of our syllabus, it's important to understand how and why we're able to compare the brightness of stars by absolute magnitude, even though each of the stars are different distances away. Essentially, if we are able to analyze the temperature and absolute magnitude of a star, it gives us information about the star's size. And this is where HR diagrams start to come in. In these diagrams, you'll see that there are essentially 4 axes which are being labeled. There are 2 y-axes and 2 x-axes. However, it's important to note that each pair of axes are quite closely related to each other. So for the y-axis, you'll generally see absolute magnitude and relative luminosity both being displayed. They're essentially both measurements of brightness, they just work in different scales. And for the x-axis, we have surface temperature and spectral class. The spectral class are given as letters, and in some HR diagrams and other information that you might see in stars, you might see that beyond those letters, there may be a number that goes with it as well that becomes a little bit more specific. But these spectral classes or these categories of stars are all based on surface temperature. So we can kind of plot and scale both axes together in our diagram. A key feature that you'll notice is that most stars, when plotted, fit along this diagonally running line here. And this is what we call the main sequence. Most stars are identified as main sequence stars. They follow the general trend that as the surface temperature of the star increases, the absolute magnitude or the luminosity of the star increases as well. For stars with low temperature and low luminosity, what this suggests is that the object has low mass. Why? Because stars with low mass are unable to release the volumes of energy which are released by larger stars. And so conversely, stars which are luminous and have higher surface temperature mean that lots and lots of energy is being released from that star. And this is due to the fact that there is lots and lots of mass, that they're leading to large numbers of fusion reactions happening, per second or per unit time. However, you'll notice that there are some other classes of stars which exist as well. We've got our giants and supergiants in one of our opposing corners, as well as white dwarfs in our final opposing corner. For our supergiants and giants, we see that they are low temperature, but they're still really, really bright. So even though one section of the star might be, relatively speaking, quite cool, lots of energy is still being released in total. So even though it's cool, it still must mean that the stars are quite large. We also have the white dwarfs, which are kind of the opposite. They have lots of temperature, but they don't release a lot of light. What that means is that even though the stars are really hot, there isn't much energy that's being released by the star in total. So even though the star itself is quite hot, because it's not releasing a lot of energy, it must be small and there mustn't be a lot of mass there. We call these the white dwarfs. In our previous video, we talked about the idea that higher temperature stars were CNO cycle dominant. And this is because the fusion processes that occur in the CNO cycle are facilitated by having high energy protons, which are able to overcome the Coulomb repulsion of our larger nuclei that it has to interact with when compared to the small nuclei involved in the proton-proton chain. And we can actually see this trend in our HR diagram when looking at main sequence stars, as we see higher surface temperature stars having CNO cycle dominant nuclear processes, whereas some of our smaller stars are more proton-proton chain dominant. And then we sort of have a middle ground section of the main sequence as well, where there is, relatively speaking, equal or even amounts of both the proton-proton chain and the CNO cycle occurring. So I've been talking quite broadly about how stars have different sizes and release different amounts of energy and relating it to the HR diagram. But I want to also have a look at the idea of the factors and the variables which dictate the size and energy of the star. In summary, if you are a star and you have more mass, then that's going to mean that there is more gravitational force applied to all the mass on the star. What that's going to mean is that there's going to be more pressure that pushes in on all of the particles, and that essentially encourages nuclear processes to occur. This is what makes a star release lots of energy and undergo fusion in the first place. The extreme clustering and pushing in of all of those particles leads to that fusion. However, that fusion, due to mass defect, means that there is a release of energy. And so that release of energy puts outward pressure on the edges of the star, kind of like air in a balloon. And so you've got these two forces. You've got gravity trying to collapse all of the matter inwards, and the release of energy through fusion, which is creating outward pressure working against the gravity. Essentially, these two forces are going to end up finding a point of equilibrium, where the push of gravity is going to allow the star to continue the fusion process that releases outward energy, and that outward energy is going to push against the gravity to stop the star collapsing in on itself, effectively leading to a stable radius. And that therefore will dictate the size of the star. For stars with more mass, the gravitational force is going to be higher, but so also is the pressure. And effectively what that's going to mean is that the equilibrium point is going to exist at a larger radius. And so to finish up too, we'll talk very briefly about star life cycles as well, and sort of connect it back to some of the types of stars that we saw in our HR diagram so that you can get a little bit of a concept around the age of the stars at different points in the life cycle. So stars first are created in what we call a stellar nebula. These are clouds of material, generally speaking, most commonly hydrogen and helium, but other particles potentially too. And this cloud of material collects together and holds together through gravity. And there'll be pockets of the nebula that start to collapse in on itself and get heavier and heavier and heavier. And the heavier one of those little clusters is, the more matter from its surroundings it will start to pull in. Eventually, this collection of mass is going to get large enough where there's going to be the beginnings of fusion processes happening in the cluster. Those fusion processes again will release energy, and eventually this collection of mass is going to reach a point of stability where it's now formed a main sequence star. And what type of main sequence star it is really just depends on how much mass is present. Most main sequence stars will form into low mass stars, and let's talk about their life cycle first. When these stars get towards the end of their lifetime, there is quite a large release of energy, more than the usual pressure that led to equilibrium as previously. And so what that will do is increase the radius of the star itself, forming a red giant. That matter is getting pushed and pushed and pushed and pushed further outwards, and essentially the matter never then collapses back in on itself. And so the outer edges of the star become this big cloud of stardust and forms what we call a planetary nebula, where the outer edges of the star form a very large cloud, and you may or may not be able to see it on the video, but on the very center of this diagram there is a little tiny white dot. This is what we would call the white dwarf. It's the core of the star. It's what's left over. It's not very big at all, but it's still really, really, really hot, right? Because it was the hottest part of the original star. And so this small white dwarf exists really hot, but it gives off a lot of thermal radiation and loses a lot of its energy over time until it stops glowing and essentially becomes what we call a black dwarf. This is a cooled core of a star. For high mass main sequence stars, at the end of their life cycle, they undergo a similar process to the low mass stars. There's a larger than normal release of energy, forming what we call a red supergiant. It's similar to a red giant, but because we started with more mass, these guys become quite a lot bigger. And so all of this matter is expanding outwards and outwards and outwards. But for high mass stars, what can happen is that all of this mass stops getting pushed outwards and gravity takes over, becomes a more dominant force, and all of the matter begins to collapse in on itself. And so there's this big crushing effect, and all of the matter is squeezed in together more than they usually would in the main part of the original star's life cycle. And this additional energy, like we were talking about a little bit earlier in a previous video, when we go supernova and this crushing and high energy situation occurs, elements heavier than iron can begin to fuse. Essentially, we supply the energy for an endothermic process to produce what would usually be quite inefficient, which is nuclei with lower binding energy per nucleon than iron. The remnants of the supernova will leave us with what we call a neutron star, which can, but not always, but can then form a black hole. Thank you very much. In the next video, we're going to pivot a little bit and move on to a slightly different concept. Our focus will be on the standard model of matter. We spent a lot of time already focusing on the building blocks of the atom and how matter is composed, but the standard model is a much more complex version of what we have discussed already, but is a much more modern and accurate representation of matter itself. But until then, have a good one.